What's up, physics? Welcome back to the dirt bike shed. We're going to finish springs here. There's another video on springs where we talk about F equals negative kx. So this is the second spring video, or maybe even the third, but make sure you watch the other spring videos before you watch this. All right? Now, here's a review. We've got this spring. Now, you're like, that's not a spring, it's a bungee cord. So what? It's elastic, okay? So we have this elastic object, and we can pull it, and it'll stretch, right? So we can quantify its ability to stretch in the letter K, all right? K is how many newtons it takes to pull this bungee 1 meter. Now, this bungee itself might not stretch a meter before it breaks, but the idea of this is in the working range of this bungee, how hard is it to pull? So the formula is F is equal to negative kx. So obviously F is in newtons, and x is distance. So K turns out being newtons per meter. Does that make sense? So what we're going to do today is continue talking about springs, and we're going to talk about this part now. We pull it, but what else happens? Well, it pops and we get energy back out of it. So however much force you apply, there's a formula that relates to how much energy is released, right? What two things are going to be equal here? Not force and energy. What two things are going to be equal? All right? Now, the choice you should choose would be work and energy. And we learned that earlier, okay? Work and energy are both measured in joules. So when we talk about how much work we do to this spring, right? How much work we do to it, that's how much energy we're going to get back out of it, okay? So it's the same thing. So let's talk about why the formula for work on a spring is not W equals FD. It's not. Let's talk about that. All right, now the reason our formula is not W equals FD for a spring, that's not the work on a spring, is check out my man from Slow-Mo Lab. This guy makes some great videos, and he's pulled a rubber band here, right? A rubber band is elastic. And if we were going to say that the formula for this rubber band or for a spring, hang on, let me fix this. There we go, that's better. If we were going to say that the formula for a rubber band was work equals force times distance, then this would have to be true. When you had the rubber band and you pulled it, if you let go of it, it would have to stop here. Now, that's not what happens, okay? Check this out. When you let go of a rubber band, it's going to go past that point, right? Naturally. And the rubber band obviously isn't the best example. A better example would be like a bent ruler. Or even better than a bent ruler, how about this saw? Got this saw here, right? Straight up and down. Now, if I could use the formula W equals FD, that means when I bent this saw, see now it's elastic in this direction, right? When I bent this saw, if I let go of it, it would have to stop right here for the formula to be W equals FD, force times distance. What happens, though, when something's elastic and you pull it, it goes past the point, right? When I let go of this, it goes past that point. If I had a better hold on this, it'd be better, but when I let go of it, it's going to go on past the middle point. Don't you agree? If I was doing this in slow-mo, I would let go, and then it would go past the middle, and then it would go all the way over here, and then it would come back. Does that make sense? So there's a different formula. Here's the formula. The formula for doing work to a spring is the amount of work that you can do on a spring is equal to 1/2 kx squared. And you may be like, no, Mr. Perkins, the formula for work is W equals FD. Okay. Well, what is the F on a spring? Isn't F equal negative kx? And isn't, so there's our F. And isn't D really x? So you'd say the work was equal to negative kxx, where work is equal to negative kx squared, right? Mr. Perkins, where does the half come from? Remember when I had the saw and I bent the saw like this, right? Well, when I let it go, it's going to go twice that distance, right? It's going to flex up to straight. It's not going to stop here. It'll flex all the way over here, and then it'll go back. So that's where the 1/2 comes from. So now here is our formula for doing work to something like a bungee. And isn't work equal to energy? And isn't work equal to kinetic energy and potential energy? And all these things are measured in what units? What are the units for work and energy? Gosh, I hope you don't miss this one. It's joules, right? Joules. So the force applied to a spring is equal to negative kx. That's from our last video. And then when you do work for a spring, the amount of energy you put into it is equal to the amount of energy you get out of it, because that's how physics works. So the formula for work or kinetic energy or potential energy is 1/2 kx squared. And there's all sorts of things we could apply to this, okay? We could say you did this much work to a spring. How fast will it shoot an object? Okay, I did this much work to a spring, 1/2 kx squared. How fast will it make an object go away? What is the formula for kinetic energy? 1/2 mv squared. Mr. Perkins, what is this thing? You're talking about doing work to an elastic object and then calculating how fast a massive object would be shot away. What sort of weapon could that be? If you don't know the answer, you've never been an 8-year-old boy, because the answer is slingshot. Yeah, that's how a slingshot works. Now, here's a slingshot that I built. It's a big slingshot, right? The pull right here. When I let it go, I can launch something that way. Now, the force in this situation is applied in this direction, and the elasticity is here. So we would have to do some trigonometry, and this would be the hypotenuse of the triangle over here. This would be the hypotenuse of the triangle. But you get the idea. The amount of force or the amount of energy that I put into this slingshot is going to be equal to the amount of energy the object has when it leaves, correct? So we got to find something to shoot with the slingshot. But before we shoot it, I'm going to have to do a little repair to it. And I'm going to have to wear some glasses because bungees sometimes snap, and that's dangerous. All right, so what I decided to shoot was a paintbrush, because the brush will fold over the elastic part of it, and then this is sort of like an arrow. I don't know. It's something I figured I could shoot now. There's a lot of things we can find out here, but let's just watch it happen. Okay, now for us to find out how fast that brush went, we would have to know how hard I pulled on the spring, the K of the spring, and how much the brush weighed. Does that make sense? Let's think about it. All right, we're looking at a top view of the slingshot, and what you didn't see was I went out there with a spring scale and I pulled in this direction with my spring, pulled in that direction, and I found out that it took me 18 newtons of force, and I pulled that spring back 1 meter, okay? So if F is equal to negative kx, then the K of this spring is 18 newtons per meter. So that is the K of the slingshot. Does that make sense to you? I pulled this back, you saw me in the video, pulled this thing back 1 meter. And it took me 18 newtons of force to do that, okay? So now we're going to do some new math. The work that I did pulling that spring back is equal to 1/2 K x squared, right? Or the work I did to it is also equal to the potential energy that I stored in that spring. So 1/2 of 18 newtons per meter. And I pulled it back 1 meter. So the work that I did to the spring, you calculate that for me. 1/2 of 18 times 1 squared. I did 9 joules of work to that spring. In other words, I stored 9 joules of energy. And then after I stored those 9 joules of energy, then I let go of it, right? And it went pew, and it went flying away. Now, how much do you think that paintbrush weighed? I'm going to tell you that paintbrush weighs about 0.5 kilograms. All right, that's a very accurate guess. So if the work I did was equal to 9 joules, then the amount of kinetic energy I'm going to get out of the spring is also equal to 9 joules. What is the formula for kinetic energy? It's 1/2 mv squared. So the 9 joules is going to be equal to 1/2 the mass of the brush is 0.5 kilograms. So what was the velocity? We've got to solve for that v. I'm going to let you do that right now. What was the velocity of the paintbrush at its maximum velocity as soon as it came off of the bungee? That's that v. Okay, let's solve it together now that you made your guess. 1/2, I'll move it over here. That makes it 18. 0.5. I got to move it down here. That makes it 36. So 36 is equal to v squared, right? Just doing some 8th grade Algebra 1 here. And if 36 is equal to v squared, then v is equal to 6 meters per second. And if you watch that video, that is all very, very accurate. I would say that the velocity of that brush when it came off of the slingshot was 6 meters per second. I'm going to give you some more problems in the next video. And peace out from the Dirt Bike Shed.